Thank you very much for the introduction. So I will present today our work, reasoning about explanations for non-validation in SHACL. This is joint work with Robert David, Magdalena, Axel, Polleres, Bojken, Shehu, and Mantas. So I'll start by first providing some intuition of what SHACL is, some introduction to SHACL, and then I will jump to our work. I guess we're all familiar with RDF and OWL, but I will very briefly go through them. So RDF is a standard data model for representing information in the semantic web. And since it was standardized in 2004, it has been widely adopted, and there are large superstores. But unfortunately, there are large superstores in the web, but unfortunately, they may be incomplete or incorrect, and this is often the case. Now, to address incompleteness of information of RDF graphs, W3C standardized in the same year the web ontology language, which, as we know, is based on expressive description logics and makes the open world assumption. But unfortunately, OWL is not always suitable for checking correctness of the data, and this is expected and understandable because it was not designed for this. Let us illustrate this with an example. Assume the data is stating that margarita has 3 ingredients which are vegetarian. And the ontology states that a pizza is vegetarian if all its ingredients are vegetarian. Now, if we want to conclude or to check whether margarita is a vegetarian pizza or not, if we would expect that that we can conclude that margarita is a vegetarian pizza, but unfortunately, under the open world assumption, we cannot do this because there may be a world in which margarita is a non-vegetarian ingredient. Now, on the other hand, data correctness gained ground as a normative aspect in RDF-based applications, and it became increasingly important to have a suitable and standardized language that checks the quality of RDF graphs. And for this reason, W3C standardized in 2017, some years ago, the shapes constraint language, which is essentially a constraint language for checking conformance of RDF data. As we will see later, this is closely related with description logics and OWL, but unlike them, it makes the closed world assumption. But what is the syntax of SHACL? In SHACL, there are 3 disjoint sets of predicates: class names, property names, and shape names. Class names and property names are the usual ones that we have from OWL and description logics. They are the predicates that occur in the RDF graph. But there is this additional third set, which is shape names, which are essentially unary predicates like class names, but they just should have a different name. They should be disjoint in a set of class names. Now, what is a SHACL constraint? Is a formula of this form, S if and only if phi, and intuitively this means that the shape name S is defined by this shape expression phi. And this shape expression phi may be a complex shape expression that may contain top or class names or shape names or class names or constants. It may contain conjunction, negation, regular path expressions, qualified number restrictions. So as you can see already here, a shape expression is very similar. One can view it as a description logic concept, actually an expressive description logic concept that can even go beyond ALC-IQ. Okay, an important notion in SHACL is that of a SHACL document. What is a SHACL document? Is a tuple that consists of a set of constraints C and a set of target atoms that need to also be satisfied by the data graphs. What are these target atoms? Are essentially a set of shape atoms that are formed from the shape names and nodes of the graph. Now, to understand validation, what is validation? Because that's the crucial task in SHACL. I want to define the notion of validation, or to explain the notion of validation here with the perspective of description logics. Now, a set of constraints C can be viewed as an expressive description logic terminology extended with closed predicates. Expressive, I think we understand why I already explained it, because shape expressions can be viewed as expressive description logic concepts. Terminology, because constraints can be viewed as definitions, as concept definitions in description logic terminologies. Concept definitions of the form S is equivalent to phi. Now, if you think of this terminology that we created from the set of constraints C, in the left-hand side of these concept definitions, they are shape names, and they should always be open predicates, but all the other predicates are closed predicates. Now, what is a closed predicate? A closed predicate is a predicate whose extension should not be changed. It should be fixed as it is given in the data graph. So as you can see here, class and property names will be closed predicates, meaning the predicates that occur in the data graph should remain, their extension should remain exactly as they are given in the data graph for interpretations. Now, what is validation? A graph validates a document CT. This validation here can be viewed as checking satisfiability of a DL knowledge base, where the A box consists of a graph of the input graph and the input set of target atoms that we need to also verify. And the T box is essentially this DL terminology that we created from the original set of constraints. But when we pick interpretations should be over fixed domains, over a fixed domain, which consists of the set of all nodes that occur in my data graph, in the input data graph. Now, what does it mean? Intuitively, it means that to check whether a graph validates a shackled document CT, we need to check for an extension of G union T with shape atoms that are formed from these shape names and the nodes that occur in the graph in such a way that this extension now satisfies this terminology CT. It was shown in 2019 that validation is NP complete in both data and combined complexity, and this is an important result for us because we will use this result for our results that we have in the paper. If we go back to the previous example, now we can easily conclude that margarita is a vegetarian pizza because again, here has ingredients and vegetarian are closed predicates, their extensions are fixed, so it must be the case that margarita is a vegetarian pizza. I hope that now we have an idea of what SHACL validation is. Now, why explanations? Why do we study the topic of explanations? The reason is that in the SHACL specification, a very important notion is that of validation reports. Now, what are validation reports? They aim to explain the outcome of validating a graph against a SHACL document. Intuitively, what it means is that if an RDF graph validates a SHACL document, then it should return yes. If it does not validate a SHACL document, then it should explain why this is the case and provide ways to fix this so that we can regain validation. Although this is an important notion for the SHACL specification, the standard leaves it open on how to provide such explanations to the users. And this is exactly the open problem that we tackle in our paper. We propose a notion of explanations here that is based on logic-based abduction and database repairs. Now, intuitively, what are database repairs? Essentially, given a database that does not satisfy a set of constraints, a repair in databases is usually given as a set of atoms, facts that are added or deleted in the input database so that the repaired one satisfies the constraints. And this is the idea that we also use for defining explanations for SHACL. More formally, we define the notion of a SHACL explanation problem as a quadruple consisting of a graph, a set of constraints, a set of targets, and a set of hypotheses. The set of hypotheses is essentially a finite set of atoms. There's another RDF graph that is disjoint with the input data graph. Now, what is an explanation for us in this setting is a pair that consists of A and D, where A is a set of atoms from the hypothesis that will be added to the input data graph, and D is a set of atoms that will be deleted from the graph in such a way that the resulting data graph should validate the document. So as you can see, it's the same flavor as the notion of repairs in databases. So explanations for us are given in terms of how to repair the data so that we can reach validation. Of course, there may be exponentially many explanations. So here, like in databases, we also focus on two typical preference orders over explanations: subset minimal explanations and cardinality minimal explanations, which intuitively aim to provide explanations that minimally change the input database. Let's illustrate this setting with an example. Consider the step where the graph states that Ben is enrolled in C1. The constraint states that students are defined as all those that are enrolled in some course. We want to verify whether Ben is a student, and the hypothesis has two facts that C1 and C2 are courses. Now, one can easily see that the graph does not validate C and T, and the reason is that enrolled in and course are closed predicates, and in order to be able to satisfy student Ben, we should have had course C1 in the database, in the graph, in the input graph. But this is easily solvable because course C1 occurs in a set of hypotheses, so here we can provide an explanation, actually the only explanation, which sets D to the empty set. So we do not delete anything from the data, but we add one fact of the data, which is core C1. And of course, now the new graph will satisfy a set of constraints, this constraint, and it will include student banning. So after defining the notion of explanation, the next step for us was to identify a collection of reasoning tasks that is meaningful and helps us understand explanations in the context of SHACL. And for this, we define 6 decision problems, which are essentially based on the typical decision problems, typical reasoning tasks that are studied in logic-based abduction. The first one is recognition of an explanation. So given a tuple, is it an explanation for the input set? Existence of an explanation. Does there exist an explanation for the input set? Or 3 and 4 are essentially checking whether given an atom, given a fact, is it a necessary addition for the input set? Is it a necessary deletion for the input set? And of course, also relevance. Is an atom a relevant addition or a relevant deletion for the input set? We study all these 6 problems in 3 variants for each problem, the variant without the preorder and the variant with subset minimality and cardinality minimality preorders. And for each of these cases, we study the data and combined complexity. I think I have around 2-3 minutes left, so I will provide a summary of the results here and invite you to the poster for more details on the results. So we study the data and combined complexity of all the reasoning tasks. And what you observe is that we obtain a range from NP completeness and co-NP completeness for most of the reasoning tasks to the second level of polynomial hierarchy for some tasks with preference orders. And this is intuitive because now when we want to check for subset minimal explanations, we need to call an oracle to make sure that there is no smaller explanation. For instance, if we go back to this example, to relevant, to check whether an atom is a relevant addition for the input set, what needs to be done to show the upper bound is to first guess a tuple AD that contains this atom alpha, then check that it is an explanation. This can be done in MP. And then we also need to call a co-NP oracle to check that there is no such a smaller explanation that also has the atom alpha. And this is natural. We show that we have the same data and combined complexity for all of the reasoning tasks. We show the upper bound in combined complexity and the lower bounds for data complexity. Next, what we do is we study a non-recursive case. Non-recursive case is very important for SHACL because actually the standard defines the semantics only for the non-recursive case and leaves it open for the recursive case. We study both combined and data complexity also for this setting, but we need different, and we show that we have the same combined complexity as for the recursive case, but we need different proofs for the lower bounds because here we show the lower bounds for data complexity and there we heavily employ recursion for showing, for doing the constructions. But what is nice here is that for data complexity, we also reach some tractability results. I think for the recognition, for the problem recognition, we have P time complete for data complexity, and we actually are even able to show that validation for the non-recursive case is also P time in data complexity. And finally, we also study a more general setting with explanation signatures. And why is this the case? Well, the user may want to specify that some predicates are read-only, add-only, or delete-only, meaning that the explanation should not maybe touch such predicates, or they should not be adding atoms over these predicates to the data or deleting atoms of these predicates to the data. And what this will do, it will filter out even more undesired explanations, maybe even from subset minimal or cardinality minimal explanations. So we studied both data and combined complexity for also this more general setting for both recursive and non-recursive case. And we show that more or less all the results for usual set hold also for this more general set. So this concludes my talk. Thank you very much.